Hi, welcome back. In this lesson, I'm going to be showing you some example proof trees for propositional logic. We have introduced the tree rules in the previous lesson, and now we're going to look at a few examples of how the rules get applied to reason about arguments. With this first example, I've got a tree we're going to produce a tree for the argument from the premise P implies Q or R implies S to the conclusion P or R implies Q or S. And the way that we use the tree rules is we check and see whether we've got a counterexample to the argument. And that involves writing down the premise and the negation of the conclusion. So in this case, what I have is the premise, P implies Q or R implies S, and the negation of the conclusion, so we write down not P or R implies Q or S. And the tree is going to try and show us whether there's a way of making these two things true. So could you have the premise true and the conclusion false? So in this case, I'm going to process the negated conclusion because the result of processing this is two formulas that don't branch. In this case, it's a negated conditional, so I write down the antecedent, P or R, and the negated consequent, not Q or S. So now I have three formulas left in the tree that haven't been processed. The premise, P implies Q or R implies S, and now these two new formulas here in red. This formula, which we've processed, has got a tick behind it saying it's been done and we don't need to extract any more information from that. So I can process either of these three formulas. My choice, all of them will give me the right answer. In this case, I'm going to process the last formula because, again, this formula is going to result in two new formulas, but the tree is not going to branch. If I process the P or R, I get two options, a P branch and an R branch, and then I'd need to keep processing in two spots. I'm lazy, I don't want to do that, so I'll process the not Q or S, and I will get not Q and not S. Negated disjunction, that means both of the disjuncts have got to be false, so I write down not Q and not S. Again, that gets a tick, and so I have the premise still left to do, this P or R left to do, a not Q and a not S. So now it's much of a muchness what to choose, so I'll start with the first one. P implies Q or R implies S, I tick that, and I get two branches. P implies Q branch is one option, that's one way for the disjunction to be true. The R implies S branch is the other option, it's the other way for the disjunction to be true. So now I've got these two branches left. And now I've got the formula P or R left to process. The not Q can't have anything to do with that, it just says Q is false, that's left. The P implies Q and the R implies S, that's what's left. So let's start with the P implies Q. I write down not P and not Q, but I only do it in this branch because it's only in this branch on the left that the P implies Q is taken to be true, so I only put its results in this branch here on the left. I don't write it down here over on the right because that branch doesn't take P implies Q to be true. So now here in this branch, I've got the P false option and the Q true option. And you'll notice that one of these is not like the other one. Q here, we've said that Q is true, and if I trace back up the branch, I've said P implies Q, I've said that S is false, and I've said that Q is false. So I've got this clash between the not Q and the Q. So those two can't be true together, and so I'm going to close that branch. But instead of closing that right now, I'll process the right branch. I'll get the R implies S, not R, and S. So I've got not R and S in the right branches, I've got not P and Q in the left branch, so let's start with the closing. First, I'll write down this X under the Q because it closes with the not Q, and we'll notice here we've got the same sort of thing happening in this right branch over here. I've got the S and the not S, so I'll close those. That branch closes because I can't have S true and S false at the same time. But these other two branches are finished. They're left, except we've got this P implies R, P or R, sorry, left to do in this tree. So let's process that. I'll process that, and I get P or R branches here and here. I've got to add them only to the open branches that I've got left, and now we can see we've got some more closing happening. I've got a P and a not P, so I'll close those two, and I've got an R and a not R, so I'll close those two. But what I've got left is two branches now where if I trace all the way back up any of the complex formulas have been processed. There's no information left to extract at all. So what I've got left is two open branches. We know straight away this argument is invalid. These two branches show us that there's two different ways of making the premise true and the conclusion false. But we're not going to stop there. Let's focus on one of these open branches and see what it says. So what I'll do is I will pick one branch, and let's pick the left branch, and I'll just write a green ring all around it to make clear the formulas that are in that branch of the tree. Remember, a branch is a path that takes you all the way from the top of the tree to the bottom, to a leaf in this upside down tree that we've got here, and you follow the path backwards, never doing any backtracking. That's what we call a branch of the tree. And this branch is one way that things could be that make everything in that branch true. So in particular, it makes the premise of the argument true and its negated conclusion true. So it makes the premise true and the conclusion false. So let's see what the branch says. First, about P, it says not P. So according to this branch, we can interpret B as being false. And it says not Q, so we can interpret Q as being false. And it says R, so it interprets R as being true. And it says not S, so it interprets S as being false. This is the interpretation that we get from the open branch. And when you look at the premise and the conclusion of the argument, you'll indeed see that the premise turns out to be true. I could just plug these values straight back into the premise and see that if P is false and Q is false, then P implies Q is true. If R is true and S is false, then R implies S is false. So one disjunct is true, the other disjunct is false, so the whole disjunction turns out to be true. So the premise is indeed true, and if I look at P or R implies Q or S, I see that P or R is true because P is false and R is true. And I see that Q or S is false because Q and S are both false. So in this case, the conditional turns out to be false. So the premise is true and the conclusion is false, and the argument is indeed invalid. We've shown that there's a row of a truth table which makes the premise true and the conclusion false. And we've done that by constructing this tree, rather than having to go through all of the 16 different rows of a truth table. And so we've got one row here, one branch which makes the premise true and the conclusion false, and I'll leave it to you to have a look at this branch and see how it's a different way of making the premise true and the conclusion false, because it gives you different truth values, at least for P and not R. So that's one example. Totally thoroughly worked out, which shows you how to use the tree rules to evaluate an argument. Let's go on to another example for you to try. Instead of asking you to work through an entire tree, what I've done here is I've produced a tree for you, except maybe I've made a mistake. Maybe I haven't. Have a look through this tree and let me know, answer the question, is this tree correct or not? Is there a mistake in the tree? Or is the tree correct and actually every branch closes? Or is it correct and when you check it you see that there's an open branch? Have a look, have a think about this, and then register your result and see how you go. So, how did you go? Post in the forums, or if you've got any questions, and I'll check in and see how everyone's going. Let's look at another example. Here's another tree. This time it's going to be a tree for the argument from P implies Q or R to P and not Q implies R. So again, we'll start with the premise and the negation of the conclusion. And again, we've got two different formulas that we can process. And again, I'm going to choose the negated conditional because it doesn't branch. In this case, I write down P and not Q, that's the antecedent of the conditional, and I write down not R, that's the negated consequent, because we want the antecedent to be true and the consequent to be false. Now I've got two formulas left to process, the P implies Q or R, which branches, it's a conditional, and the P and not Q, which is a conjunction, which doesn't branch. So I'll choose that one to process, and I write down P and not Q. So now all I have left to process is the P implies Q or R. Nothing is closed yet. I've got P not Q, and not R, and no other clashes in the tree. So when I process the P implies Q or R, I get two branches, not P branch and Q or R branch. So I first notice that the not P branch closes because I'd already written down P. So that branch is left, closed, nothing left to do there, no possibility of it being true, and I've got Q or R left in this branch. So I'll process that, and I get a Q branch and an R branch, and now I can see the Q clashes with the not Q, and the R that I've got here clashes with the not R that I've got there. So in this case, the tree started with the premise and the negation of the conclusion, and as I processed it, got some different possibilities, and none of them worked out. There is no way to make these two formulas true at the same time, so there's no way to make the premise of this argument true and the conclusion false, so indeed the argument is valid. This is a valid argument because the tree for the premise and the negation of the conclusion closes. So that's a valid argument. Let's move on to another example for you to try. Here, I've processed the tree, and this time, instead of leaving it unexplained, I've even written down here that this branch is open and these two branches are closed. But again, you shouldn't trust me. I want you to check this tree and see, is there a mistake in it or is it correct? And if the tree processing is correct, is every branch actually closed? Did I just make a mistake with the indicators down the bottom here? Or is it correct and is there a complete open branch? Take a check, have a vote, and then see how you did. And then I'll check and see how you're going in the forums if you've got any questions. Here's the last example for this lesson. And this example is going to be a little bit more complicated because I've got a little bit more complicated formulas. These biconditionals in the premise and the conclusion are going to branch whichever way I process them, and they're going to produce quite a wide tree. So let's get going with this. Again, with this tree, I write down the premise and the negation of the conclusion. And now, a biconditional, when I process it, it branches. Negated biconditional, when I process it, it branches. So I'm going to have branches either way we go. So here it is. The premise, P if and only if Q or R, when I process, produces these two branches. One where P and Q or R are both true, and the other where P and Q or R are both false. So I write down their negations. So here I've got two branches. I've written them quite wide apart because there's more branching left to go. Next step, I look at the not Q or R, because in this case that doesn't branch, so I write down not Q and not R. But again, I only write it down in the left branch because I'm just processing this formula which just occurs in the left branch. Sorry, the right branch, right here. Next formula I process is the P and not Q if and only if R are negated. This formula here, it occurs on the left branch here, and it occurs in the right branch as well, so I've got to write down its results in two different places. And its results are these two different formulas, P and not Q and not R, or P and not Q negated and R. And so I write it down both in the left-hand side of the screen here and the right-hand side there. So when I look at this, I notice I've got a few closures. I've got a closure over here. I've got the R closing with a not R, so I can close that pair. But these three branches are left active. So as you can see, it's a pretty complicated tree. The next thing I'm going to process is this P and not Q, which occurs over here and over here. So I'll process both of them at the same time, and I'll write down P and not Q over here and P and not Q over here. In this case, the P closes with the not P all the way up there. So this whole right-hand side of the screen, whole right-hand side of the tree is now closed. But this left-hand side is still open. I've got no closures here. I've got a not R in this branch. I've got an R in this branch, but they're in different branches, so they don't close. P not Q, P, no closures yet. So let's see what next thing there is to process. I see this Q or R, and I process that. It appears in both this branch and this branch, so I write down the Q or R options in both cases, and now I get some more closures. This Q closes with a not Q, so I get a closure there, and this R closes with a not R, so I get a closure there. But these two aren't closed yet. But I'm not finished. If I look up in this branch, I see I've got Q, R, and I've got this negated conjunction formula, which is again something else that I can process. So when I process this, I get not P and not Q. Again, I write down the negation. A conjunction negated says that the conjunction, they're not both true, so I write down the negations of both these formulas. And I'm being really literal with the rules, so I write down not P and the negation of not Q, and literally speaking, that's just not Q. So I've got a P all the way up here in this branch, so the not P that occurs here or there closes with that P, so I can close both those two, but I've got these left, this formula here and this formula here. So what to do there? I can process those, I get the Q's, and I'm nearly done. I've got Q or R left. I've got Q or R processed. In fact, am I done? Yes, I'm done. These two are open branches. And so to show you in particular what formulas are in that branch, I'll try and be careful and establish one example branch that's going from the left leaf all the way to the premise. And what I get here is an open branch where I've got Q is true, R is true, and P is true. So if you go all the way up to the argument that I've got written here, I say that if P, Q, and R are true, then indeed Q or R is true. So this biconditional is indeed true, but P and not Q is not equivalent to R because P is true, Q is true, so its negation is not true, so P and not Q is false, but R, remember, is true, so this biconditional is false. So indeed, what we've done is we've got a counterexample to this argument. We've got a row of a truth table where P is true, Q is true, and R is true, that makes the premise true and the conclusion false. Now for an argument which only had 3 atoms, P, Q, and R, this was a really big tree. Just shows you some ways that trees can get quite complex, quite wide, with lots of branching. But still, if you follow the rules and follow them step by step, you will get a correct answer, even if on the way you get through and have to process quite a few formulas. So that's the last example that we'll work through here. In the notes there's some more examples, and in the forums there's lots of examples of people working through different exercises. The quizzes online have got lots and lots of different examples for you to check and to work through for yourself. So I hope you have fun with trees and use them to evaluate arguments and to analyze propositions. Check up in the forums with how you're going, and I'll see how you're going there.